All right, so we've got the situation here. Here you've actually got a moving source, so your source is moving in this direction here, all right, and it's producing sound waves. Now, as you can see, if you're over here and you're hearing this noise coming to you, these sound waves are bunched up. All right, so these are wave fronts coming past you here, and they seem to be coming pretty quick. And so what has increased? Well, what would have increased? Your frequency would have increased. The wavelength seems to have decreased. All right, the wavelength has decreased, the frequency has increased, so you hear a higher pitch. So there's an increased frequency of frequency. Now behind, if you're over there, so this is, say, for A, we've got that situation. You've got an increased frequency. For B, if you're over here, now you see that your wavelength, from your front to your front, has actually increased. Your frequency will have decreased. So your frequency has decreased. You will hear a lower pitch sound. It will be a lower tone that you'll hear. It won't be such a high pitched sound that you're hearing. You can sometimes hear that with racing cars. You've heard that before. With anybody likes Formula One racing, you hear that the change of the car as it goes past you, that famous sort of sound as it goes past. That's to do with this whole idea of what we call the Doppler shift, the Doppler effect. Okay, so when the source is coming to you, towards you, your frequency increases, and when the source is going away from you, your frequency decreases. Now it does actually work the same effect, that if you have got a moving, if the person observing, if the observer, the listener, is moving towards a stationary source, they'll have a similar effect. If you're moving towards a source, you will hear that frequency of those wavefronts. Because you're passing those wavefronts faster, you will pick it up as an increase of frequency. And if you're moving away from the source and picking up those sounds, it will seem that the frequency has decreased. So we have a formula here that we use, and it's these two over here. And so it's these two formulas over here. Actually all three of these. This is specifically to do with light. This one over here, we use this for light, because the Doppler effect, we usually call it the red shifting or blue shifting of light. That is very important. So we use that formula for light. But these two formulas over here we can use for sound. We can also use it for light also. So looking at this over here, your F prime over here is the new frequency. All right, it's a new frequency. This F over here is the frequency if both object and source were stationary. So it's a frequency if everything is stationary. And this V, if we're talking about sound, this would be the speed of the wave, the speed of the sound wave, the speed of sound. And your U is the speed of the source. Now, I'd like to ask you the question. Let's say we have got the source is moving towards us. We've got a plus minus sign over here. You've got to choose which one you would use. The speed is moving towards you. The source is moving towards you. Are you going to use plus or minus in the formula? What happens to the frequency? Increases. So what must you use? must use minus, because your denominator must be coming smaller. So when the source is coming to you, use minus. You can figure that out. When the source moving towards, where it's going to be plus if it's moving away. All right. So it's a pretty straightforward formula, and that helps us to get the new frequency that we're going to hear. Now, in this case over here, now you're looking at you've got a stationary source, but your observer is moving. So now we get the same situation. Everything is the same, except here we got the plus minus value. So can you tell me plus minus for the moving observer? Where let's have a look at you moving towards the source. It would be plus, because you need a greater. It would be greater. So now it's on the top. So that you're moving towards, and the minus moving away. All right, yeah. U0 is the speed of the observer. US is the speed of the source. V is the speed of the wave itself in stationary terms. So it's the speed of sound generally. Okay. You all okay with that? All right. Now, this formula is actually an approximation. This one over here, this one dealing with light, because we can the speed of the object or the source is usually so much smaller than the speed of light. We can do some approximations here. It becomes a little bit more complicated with light, but here you're getting this change in f is obviously the frequency change. All right, how much the frequency has changed. Here you got your v is your velocity of your star or your object, whatever is moving. C is the speed of light and frequency. Now, what they can do, you see, is, and we're going to look at this a lot, different elements will give out very specific types of light. And you can look at those in the laboratory. So when you're stationary, you can see the frequencies that this metal or this gas will emit. Now, and that can be registered. And then when we look at a star and we see these same frequencies, it's like a fingerprint. You can see, okay, you've got one there, one there, one there, but they've all been shifted a certain amount. The whole thing has been shifted. So, and from that you can get this. You can actually measure this part of here quite easily, or relatively easily. And from that, because you also know what the actual frequency is from the laboratory, because that's the laboratory value when you're stationary in relation to that, we know what the speed of light is. We can actually measure the speeds of those objects in relation to us. And that's what Hubble did. When he looked at different galaxies, he looked at the shift in this frequency, and he was able to see that everything seems to be red shifted. It was all the light. If it was yellow, it was being shifted towards a red. The longer wavelength, the longer wavelength, the lower frequency waves. And from that, was able to determine that the universe is expanding. It was a massive change in people's views at that time.